Hi everyone, I welcome you to the presentation of this lecture on loads with rotational motion. So we've got the motor here, which has a motor torque of Tm, and it has a moment of inertia, which we are calling Jm. This load is coupled to a load. This load, the first load, it has got a torque, which we are calling TL1, as well as a moment of inertia, which we are calling JL1. Then this load is connected to a gearbox, and the feather load is connected there. So this gearbox, the first gear has got the angular speed of omega 1, and the second gear has the angular speed of omega 2. The diameter of the first gear is d1, the diameter of the second gear is d2. Then the second load has got the torque, which we're calling TL2, as well as the moment of inertia JL2. So this system, we are going to derive the following formulas. Before we come to the formulas, for us to find the initial, as you can see, we've got two moment of inertia. We've got the moment of inertia due to the motor and the moment inertia of the first load. So the initial moment of inertia is gotten from here. It's basically a summation of the two, moment of inertia of the motor and the moment of inertia of the load before connecting to the gear. So J initial, or moment of inertia initial, is equal to moment of inertia for the motor and the moment of inertia for the first load. So we can derive the following formula. So the equivalent moment of inertia for the whole system is now given by the initial moment of inertia plus the moment of inertia on the loads there. So if you had another gear there and some loads connected, you just be going like that to be the moment of inertia for that load and the turns ratio on that gear. Then you square it, of course, where A is the turns ratio. It's given by the ratio of the velocities, W2 over W1, divided by the diameters. So you can either get the velocities you've been given. If you don't have these, you can use the diameters or the number of teeth for the gears, which are those. So that will be our gear ratio. And we can also calculate the equivalent torque. So the equivalent torque is given by torque of the first load plus the turns ratio times the torque of the second load divided by the efficiency of that second load, which is this one here. So with that said, let's look at an example. The figure below shows a drive system having an equivalent load torque of, so that is the equivalent load torque, 33.75 kg meter squared. Find number one, the gear ratio, which is A, and number two, the speed of the motor if the load 2 rotates at a speed of 500 revs per minute. So this is the system with the parameters given there. So for us to find the gear ratio, we can get it from here because we have the equivalent moment of inertia, which is this one here. And the initial moment of inertia can be calculated by adding those two. The moment of inertia for second load has been given there. Then we can just make A the subject. So making A squared the subject, we have that. And then when you square root that, you're going to have A basically that. When you substitute the given parameters there, you're going to have 0.5 as the ratio, okay, the gear ratio. So the gear ratio is 0.5. And then number two, the speed of the motor. Speed of the motor is basically the speed of this gear because the motor is connected to that gear. So the rotation of the shaft on the motor speed is the same as the speed of the first gear there. So the second gear speed has been given to be 500 revs per minute. So if you get the gear ratio, this time around you play with the speeds because we have the velocities. So these are the velocities. We just make omega 1 the subject of the formula because that is the gear which is connected to the motor. When you substitute the parameters there, you realize that gear 1 was rotating at 1000 revs per minute. That was the rotation of the motor. Okay, thanks for watching.